Today we're gonna rekindle your love for trigonometry. Finally, we had to lay a little groundwork. We had a little groundwork about angles. Like we need to definitely talk about angles a little bit, and we have done that now. Okay, but now it's time to talk about trigonometric functions. Now, yes. What? Yes, absolutely. I think all of us do maybe already have a little bit of a love for trig in our hearts. This diagram should be familiar all the way back to from your geometry experience, right? So
I've been trying to plot that out.
let me tell a little bit of backstory here on why trigonometry is a thing. So just recall the reason that trigonometry comes to being is that we're thinking about, we're trying to quantify in some notion similarity among triangles. So we have these right triangles and we want to talk about their similarity and we want to maybe talk about the angles in them. And so maybe a good way to quantify the similarity between two triangles is if they have the same ratio of side lengths, right? Isn't that how we quantify similarity when we're talking about triangles? It's a much bigger discussion to have around similarity, but it's a hugely important idea, this idea of ratios, of similarity. And it's bigger than a triangular discussion too. Later we'll have to do with anything at all that's changing relative to something else. Really, this could be applied to anything in terms of rates of change even, right? It's we're thinking about the slope here of something. I want to give you a little bit of a glimpse. This is a bigger idea than just solving a simple little geometry problem. So and it's also important, I think, before we talk about trigonometry, which is such a big word. When we say a trigonometric function, I think that can be intimidating. But when you just say, oh, it's just a ratio, I think that serves to demystify a little bit, doesn't it? A trigonometric function, guys, it's just a ratio. Okay, so let's just remember that. It shouldn't be scary. And these are those ratios that you probably remember, right?
Can you do a headstand and make us yell trigs or ratios?
Trigs or ratios? Yes. That's good. I'll suggest that one to Miss Getz.
No, you should balance.
No, I can do one. I can balance something on my standing something. Yeah. You already have a good way of remembering these ratios, though. Yeah. Do you remember this cute little acronym? Right? If you're not sure, if you haven't seen this before because you were deprived by your teacher of this acronym, here we'll explain it. CAH means cosine is adjacent over hypotenuse in this picture, right? We're labeling these in nice ways. So I think those are things you've thought about before, maybe. And I think you've thought about these 6 trig functions too, right? These 3 other ones. So this should just be a little bit of review. If you didn't have AF last year, these 3 functions might be new. Everyone, I feel should know these 3 functions though, right? And you might be thinking, are there any other ratios? Well, let me ask you, how many ratios can you form with 3 things? I think the answer is 6. I think we have them. I think the answer is 6, and so we have them all, right? If you want to think about a ratio of 2 side lengths in this triangle, we have a name for it, and that's all these are conventions, are names. Now there are interesting connections between these names, though. Obviously, they've been named in interesting historical and helpful ways. Maybe you already are aware of a relationship between sine and cosine, and what this co means. If you don't worry, we'll cover that soon enough. We'll realize there's a ratio. There's something going on there. The word sine comes from the word sinus, or which means cavity, and it quantifies, doesn't it, in some sense, quantify the openness of this angle, how big this cavity is, right? How do we get a really big sine ratio? Well, we open this really big, don't we? To get this thing to be bigger in proportion, as big as we can, this divided by this, right? So that's some of the etymology there. Tangent makes me think from geometry about a tangent line to a circle or something, right? Like a line that's tangent to a curve. That's what it makes me think of. So we maybe need an explanation. I see this is opposite over adjacent, but what does that have to do with tangent lines? And the answer is actually pretty nice to talk about, but I have to draw another picture for that. So maybe we'll do that soon here. I don't know where, but hopefully you understand why I presented these. Can you guys just kill the side chatter? That'd be great. Okay. The reason I presented these horizontally is because hopefully you see the ratio going between these ones here, right? Obviously, the relationship is that they're reciprocals. Okay. So let's try our hand at like actually thinking about the trig ratios in this particular setting right here. I've got a right triangle. This is also an exercise in getting you this whole unit. These whole 3 sets of trig units are, we got a side project going. We would like you to learn all your Greek letters, okay, along the way. So there's beta, right? And you can practice writing beta as you write this example down. Beta. It's kind of fun to write. And obviously our answers here will not be numbers. They'll be expressions involving x, won't they? So that's okay. That's okay. There's not a problem with that. I think I'm okay with that. And again, just I didn't make this note on the previous page, but we usually don't write out all of the word, right? We just write sine, S-I-N. Okay, so figure out what sine beta is, what cos beta is, cosine, and is beta. And you might notice there's something kind of conspicuously absent there. What would you like that you don't have? Yeah, you'd like to maybe know the adjacent side. So figure it out. In terms of x and 3, can you give me an expression for the other missing side? Of course. Keep in mind another thing we haven't mentioned yet today, but that happens to be true about right triangles. A Greek friend of yours might have helped you. What's the relationship between the 3 sides of a right triangle? Yeah, in the US we would say we need to use the Pythagorean Theorem, right? In the UK they would say we need to use Pythagoras. Like calls him back from the dead. That's what they do.
We can't do this on our own.
Anyone from the UK? You can verify that they say this. They do. They say that. They say. Well, we need to use Pythagoras here. So what is the missing side in terms of x and 3? What is it? I think I heard a cacophony of people saying this. Yes? Is that good? X squared minus 9, take the square root. Yeah? Now I think we're prepared, aren't we? To answer all the 6 questions I have listed down below. This will be good practice from the previous slide. That's it. Grant, take the first one. Tell me what the sine of beta is in terms of x. Here. 3 over x. The cosine is, Dave? Cool. Tangent is Jeffrey.
3 over root x minus 9.
X squared minus 9.
Yes.
Is that good? Terrific. What about cosecant? What's that? And the secant is Laura. Secant.
X over root x squared minus 5.
Good. And cotangent is Chefe. Yeah, this thing takes the reciprocal. Is that good? Okay. Another question we could ask, since these are in terms of x, what's the domain of these functions that you have here? What is x allowed to be here? Everything but 0? Okay, I actually disagree, but let's keep going. What about this one here?
Oh, it has to be positive.
Okay, everything greater than 0? Okay, I actually still disagree, but let's keep going.
I'm not saying everything greater than 0. I'm saying it does have to be positive.
That is true.
One of the requirements.
Okay, all right. What about this guy here? Yeah. Yeah, so this one here, the domain, if you just like show this to someone, would be, you'd say less than -3 or greater than 3. But of course, you said you insist that x be greater than 0. So taking these things together, what is our requirement for x in this set of pictures? In this picture and in these equations? Yeah, we need x to be greater than 3. Correct? Even here. Do you agree that from the picture, x definitely can't be a number less than 3, can it? It's the hypotenuse? Okay, great. All right, let's actually put an angle to it here. One of our favorites. There it is, 45 degrees. All right, so let's pretend that you don't know the cosine of 45 degrees. If you already know it, that's wonderful. But I'm not interested in like memorizing this right now. I'd like to think about where it came from. Can you rederive? Do you know how to rederive that from first principles? What the cosine of 45 degrees is? I've labeled nothing in this picture except for the 45 degree angle. That's it. That's all I've written, and the 90 degree angle. So tell me, what's the key insight in this picture? Like, what makes this triangle special? In fact, yeah. Yeah, it's isosceles. How'd you reason to that? Yeah, so this is 45 degrees, so the base angles are congruent. If you look at it this way, oh yeah, that's kind of traditional way we look at it. I think, can you convince yourself that it is isosceles? Okay, beautiful. So that's the key insight. How does that help? It might help to like put some labels to these too. You have an inroad on this, Olivia?
If it's isosceles, then cosine and sine have the same value.
Okay, that's true. So whatever we get here will be the same for this. That's good. So actually, we could write this down right away, huh? Tangent will be 1. That's true. And so is cotangent. That's good. We're making progress. Did you have an insight, Piper, or a weigh in on this? Okay. That's interesting. How did you declare them to be 1? Is that okay to just declare them to be 1? Okay. Okay. All right, I'm going to go with her on this. Do you agree? I want to make sure everyone agrees before we just go and like call them 1. Like, what if we get them? What if we get a different answer if we like call them both 10? Then wouldn't that?
Because the ratio is going to be the same.
Okay, the ratio will be the same. I mean, if you're not convinced, we could use x or something. But let's put 1 here, and then we might revisit that question in a minute. Make sure that makes sense to us. Yeah.
Then we use the Pythagorean Theorem to find the hypotenuse, which is 2.
Okay, yeah. So is this 2 then? Is that what this comes out to? I'll put a question mark here. Yeah, what'd you get? Oh, look at that. Okay. Good. I think it's root 2 as well. And just because I don't really trust Piper, if this was x and this was x, then what would this be? I would work the same problem again, but this time with x's. Okay, I just worked the problem and I get root 2x. So does that make sense? I mean, so no, let's actually go and find the cosine of 45 degrees now. I think I'm ready here. What is it, Angela? What's the cosine of 45 degrees? Yeah, it's 1 over root 2. 1 divided by root 2, which notice if you use Piper's method, you get 1 divided by root 2. And if you use our method with the x's, you get x over root 2 times x, which is still the same thing. I think I now see why, if x was anything, 1 or 10, this would always happen. Because it's a ratio, and what does x represent? If we have this here, x represents a scaling up or down of the triangle, that's all. So that won't change any of the ratios. They'll all still be similar. So I think math is still working. Great, okay. I just had to check. Just to make sure math works. Okay. And then the sign, Emmanuel? Also 1 over root 2. Which someone already promised that would happen. Yes. Piper, what about the secant? We didn't do that one yet. Yep. The secant. Root 2. And the cosecant, how about Claire? Also root 2. And we did the others here. Tangent and cotangent are both 1. Wonderful. Okay. The other special triangle that we want to bring into the picture is, of course, one of our favorites, is the 30, 60, 90 triangle. And obviously, maybe there are other triangles. You should really stop and think, are there other triangles that I could draw where I could do some reasoning to find what the exact value of the sine or cosine is of a particular angle? The answer is, yeah, absolutely, we could. But we just, these two are so low, such low-hanging fruit that it's fun to look at these and the angles do come up in life. So, again, I want to rederive these from first principles, right? So I need a key insight about this triangle. Last the one we said the key insight is kind of like that it's an isosceles triangle. That got us all the way there, and it was an isosceles right triangle. Do you know the key insight here?
Yeah, so the short lanes only have the length.
Why do you know that though? It's, I guess, the thing I want to know.
Because angles.
Yeah, I need to be convinced that that's true. She says that's half of that. You were told it by a teacher. You get to question the man, though. Yeah.
Triangle, it's half of an isosceles triangle.
You can be more precise than that, even, actually.
And that vertical line is the bisector of the top of the
Okay, that doesn't tell me that this is half of that, though. It just tells me that these are the same.
If that's a bisector, okay.
That tells me these are equal. I agree. Right? Isn't that what you said? This bisects this? So we just doubled this triangle, right? This is the key insight. And that might be all you need to get all the way in on this. Allie.
In a triangle, all the angles are
That's correct.
so if you have 60 degrees.
Though I should make you prove that maybe too. But go ahead. Keep going.
Degrees, and you also have 60 and 60, so when you bisect.
So what kind of triangle do we see here? Yeah, is everyone convinced that this is an equilateral triangle? All right, so then we'll use that together with the fact that this is bisected. So if we call this, what do you want to name this length? What do you want to call this? X? Okay, whatever. It doesn't matter. It's all going to come out in the wash, so whatever. So this is X, it's bisected, so this whole distance is 2X. And then using Allie's insight, that must also be what this is, since it's equilateral. 60, 60, 60. Equiangular implies equilateral. Great. Now I think we're finally ready to move forward. What's this side? I don't know either. Let's try and figure it out. What do we get? 4x squared. Yeah, did you get x root 3? Or root 3 times x?
Yeah.
Cool. All right. Great. I think that's all we need. Olivia, do you want to start us off with the cosine of 60 when you're ready? What is that? If we're looking at this angle, what would that be? Yeah, x over 2x, regardless of the value of x, will be 1/2. And then sine of 60, Varun? Yeah, and the x's again cancel out. In fact, that's getting a little bit annoying, so I'm gonna go with Piper's strategy in life. And just call that 1. Is that cool? Is that cool with everyone? Because this keeps happening and it's getting kind of annoying to have to think about the x's. Okay, I think I'm with you now. All right, Chris, tangent? Sorry, say it one more time. That's a 1 down there. Root 3. And the secant, so root 3 over 1. The secant is Jasper. 2. And the cosecant, Kevin. The cosecant of 60. 2 over root 3. Okay. And the cotangent, Alexis. All right, everyone good on those? Is that cool? By the way, another nice choice besides like the Piper choice would be, and I think I heard someone mentioning this, would be instead of calling this 1, calling this 1/2. Now what does that mean? Well then, don't you get this as the length? First of all, are you okay with me doing that? That certainly works. Why is that nice though? Well, now let's ask the questions again. What's the cosine of 60? It's 1/2 divided by 1, and that just like makes that's like candy for my brain, isn't it? It's like I love dividing things by 1, right? Huge fan of dividing things by 1. Okay. So do you see how that might make things nice too? But it doesn't matter. You can call it anything you want. You can call it x, and we get the same answer, right? Hopefully that always works. So whether you scale it up or down, the trig ratios remain the same. All right, let's again go back to some practice here with like some actual computations here. So I have some angle unknown to us. Cosecant of alpha is 7/4. So I happen to know that. I want to know the value of all the other ones, assuming alpha is an acute angle. So how do I even get in on this problem is I guess the first question. You let me know.
Wait, so is the angle in degrees or radians?
Not important to me actually, but it could be whatever you like it to be. It didn't actually say to find alpha at all.
Oh.
So what are you doing out there, people who are doing something? Writing down the problem. Rock and roll. No, some people are actually already into the problem and doing something. Please, what's the first like step, huh?
Well, okay, well, like, the first thing I do is find the sign since that's...
Because it's easy?
Yeah.
Okay, I like that. Because that's the first thing you thought of, I like that. Yeah, already we have 2 of the trig functions, we just need the other 4. And then what'd you do?
You draw a diagram.
Draw a picture is like totally the solution here, right? So what picture did you draw?
So you have a right triangle, and then label one of the angles A.
You mean alpha?
That. Yeah. And then you know that the opposite side to alpha is 4.
You don't know actually that it's 4, but okay, keep going.
You can say that it's that.
You can
because
say that
a
it's 4.
ratio,
Yeah.
so it's going to be the same.
So 4
The hypotenuse 7.
and 7,
Use the Pythagorean Theorem.
or 40 and 70 if you like,
That too.
or whatever. Anything that has as its sine ratio of 4 to 7 or its cosecant ratio of 7 to 4. And then and then I think the game is up, right? I mean, what's this side? Pythagorean Theorem can help us get that. The square root of something. 49 minus 16. 33? Root 33, okay. And like I said, the game is up at this point. Now we just need to write down the other 4 trig functions. Like, for example, what's the cotangent of alpha?
Your alpha looks like a fish.
It does look like a fish. That's how you should draw your alpha, as like a fish. So what's cotangent of alpha? For example, we can do them all, right? But I just want to prove that you actually know what to do here. Yeah, root 33 over 4. And then you do the other ones too. I think time won't allow us to do this last one, but it's an interesting question. I'm a little sad, but okay, whatever. By the way, this is another new Greek letter for you. This is not Y. This is a gamma. I am. It's a huge conspiracy. That'd be awesome. All right. I'm gonna sneak a letter. You have to see what it's actually.
Olivia.
Are we doing the next one tomorrow?
Oh yeah, you should retake it. Wait, Olivia.
What's up? Yeah, bring it back up here.